Good morning, everyone, and welcome to day 4 of this year's annual ICP conference. I'm Brian Alexander, the Chief Technical Officer here at IV, and I'll be moderating today. A few housekeeping reminders for those of you with us live today. Please put your questions in the Q&A box at the bottom of your screen. We'll address these in our roundtable session at the end of today's presentations. Our first presentation by Mike Booth will focus on alkalinity versus hardness. Mike is a chemist with expertise in quality control and instrumentation. His experience covers areas including ICP OES and mass spec, as well as ion chromatography and various titration techniques. Today, Mike is the technical director at Inorganic Ventures. He received a BS in chemistry from West Virginia University Institute of Technology.
Thank you, Brian. Good morning, everyone. This presentation is going to be about water hardness versus alkalinity. And this might seem like a basic topic to review, but we actually get a lot of questions about these testing methods and how to make standards and how to interpret results. So we're going to get a little bit more detail about these methods today and hopefully clear up some of those questions that you may have. So what causes the confusion in water hardness and alkalinity? Usually it's because they're both reported as milligrams per liter of calcium carbonate. And since they are two different testing methods, sometimes this can lead to that confusion where people aren't quite sure what method they need to be doing or what they need to be testing for. As we review the testing methods for water hardness and alkalinity, I would like for you to keep this question in the back of your mind. Is 100 milligrams per liter of calcium carbonate water hardness equal or not equal to 100 milligrams per liter of calcium carbonate alkalinity? We'll return to this question towards the end of the presentation and walk through it with some sample data. Again, a lot of the confusion between water hardness and alkalinity is because they're both usually reported as milligrams per liter of calcium carbonate. But in reality, they are very closely related methods, but they are very different. So water hardness is simply the measure of the concentration of calcium and magnesium present in your sample, whereas alkalinity is the measure of your sample's capacity to neutralize acid. We're going to talk more about these methods, and you'll get a little bit more detail on how to test for each water hardness and alkalinity. Testing for water hardness and alkalinity is some of the most common testing methods run on water samples. Analysts from anywhere from wastewater treatment plants to bottling facilities, even folks who want to measure the water hardness of the water coming out of their tap at home will all use some sort of testing method for water hardness and or alkalinity. When you Google water hardness testing or alkalinity testing, some of the first search results that will pop up will be some of the pictures that I've put here on the left hand of the slides. Testing methods need to be fit for your purpose. So depending on how accurate you want your results to be and what your detection limit is will really be the main factor in selecting your method. So for instance, someone who is measuring the water hardness at their house may have a very different acceptable method than say we would at Inorganic Ventures for creating a water hardness certified reference material. So in this presentation, I'm going to walk you through the methods that we use at Inorganic Ventures to produce those certified reference materials for both water hardness and alkalinity. Just a brief overview for water hardness, we do perform an assay by ICP OES. Again, since that is just a measure of the concentration of calcium and magnesium, that's very easy for us to perform, and I think at this point in the ICP conference, you guys have a pretty good idea of how to test calcium and magnesium by ICP OES. For alkalinity, since again it is the ability to neutralize acid, we do perform an acetometric titration. Okay, so let's go ahead and dive into water hardness testing. We have an example of where we've already collected some information on a water sample by ICP OES assay. And our water sample has given us the following results for calcium and magnesium. Calcium is at 15.27 micrograms per mil, and magnesium is at 7.80 micrograms per mil. Now that we have our concentrations of calcium and magnesium, we need to convert those to concentrations of calcium carbonate. And to do that, we are going to use the mass fractions of calcium to calcium carbonate and magnesium to calcium carbonate, as shown on the right-hand side of the slides. So if you walk through those calculations, you'll see that our 15.27 micrograms per mil of calcium converts to 38.13 milligrams per liter of calcium carbonate. And we can do that because essentially the math is pretty straightforward because the units are equivalent. Micrograms per mil is essentially the same unit as milligrams per liter. So let's tackle the magnesium result. We have 7.8 micrograms per milliliter of magnesium. That's going to convert to 32.12 milligrams per liter of calcium carbonate. Now that we have those values, we simply add them up and get our final result for water hardness as 70.25 milligrams per liter of calcium carbonate. Now that you've seen the full calculation, I did want to share with you a little calculation shortcut that we use in the lab at Inorganic Ventures. Essentially, if you look at those mass fractions and round to 2 decimal places, as the shorthand in the lab, we will use this to calculate water hardness. So simply, if you want to convert from calcium to calcium carbonate, multiply your calcium result in ppm, weight volume, by 2.5, and multiply your magnesium result by 4.12. And if you add those two results together, you'll end up with your water hardness. And so just a little shortcut so you don't have to walk through the full calculations. Okay, now that we've reviewed water hardness, we're going to dive into alkalinity testing. And I just wanted to sort of review our quick method that we'll use in the lab when we need to certify a product for alkalinity. So we'll walk through our quick method here. The first step is to measure an appropriate amount of sample. So again, you'll want to have sort of if possible, a rough idea of what the alkalinity value may be, so that you're measuring out an appropriate amount of sample to titrate. Once you have that sample, you want to titrate using a low concentration hydrochloric acid titrant. Low concentration is kind of key on this. You don't want to overshoot your titration, and we'll get more into that later in the presentation. First, you want to titrate to a pH of 4.5. So you want to monitor this titration with a pH meter, and you're shooting for an endpoint, the first endpoint at 4.5, and then you want to measure the amount of titrant it took you to get to pH 4.5. And from there, you'll measure a second endpoint. So you continue your titration after you've measured your titrant, the amount of titrant it took to get to 4.5. You'll want to continue the titration until you reach a pH of 4.2, and then measure the amount of titrant that it took to get you there as well. So you might be asking yourself, why do we titrate to two different endpoints, that 4.5 and then 4.2 endpoint? The answer for that comes out of Standard Methods 2320B. So essentially there are two different calculations that you can see on the slide. One for when your total alkalinity is greater than 20 ppm, and one calculation for when your total alkalinity is at 20 ppm or less. So that distinction in the amount of titrant, and actually in Standard Methods it just says that you need to titrate a 0.3 pH difference, but we've chosen 4.5 and 4.2 as our sort of in-house method that we use at Inorganic Ventures. But if you go through and read Standard Methods, it gives you a little bit more background as to why you need to have two endpoints. Again, if you have a really good idea of what the alkalinity you're expecting, then you may not need to take that second endpoint if you're expecting a total alkalinity value above 20 ppm. As we take a look at the calculation on this slide, I did want to highlight this factor of 50,000. So in both calculations, you multiply by a factor of 50,000. And I know that internally there's been some questions about, okay, why multiply by 50,000? It doesn't seem to make a whole lot of sense just taking a look at it. So we're going to dig a little bit deeper into what that factor of 50,000 is really made up of. Okay, so in this slide I've kept the same calculation for total alkalinity that you expect to be greater than 20 ppm. So we can take a look at where that 50,000 slots into the equation. But really the 50,000 comes from the equation that you see on screen that I've tried to color code for you. So it's really 100 multiplied by 1,000 divided by 2. And essentially those terms track towards 100 is the approximate molecular weight of calcium carbonate. It's not exactly 100, but it's 100. It's very close to 100. 1,000 is a unit conversion for molarity. So since we have molarity is usually moles per liter, and we work in terms of milliliters for our sample and our titrant. There is a unit conversion there for molarity. And then we're dividing by 2 because actually since we're looking for, as milligrams of calcium carbonate, carbonate is a diprotic base. So next we're going to talk a little bit more about the diprotic base and how that affects our titration. Okay, so what we have on the screen here is a titration curve of sodium carbonate. And again, I want to talk a little bit more about carbonate and this term diprotic base. So essentially what that means is it will take 2 H plus 2 molecules of acid to titrate 1 molecule of carbonate. So if you run through the titration, full potentiometric titration of, say, sodium carbonate, you should wind up with a curve that looks very similar to this. You'll see a first equivalence point at pH of 8, and then a second equivalence point around pH 4.5. So that second equivalence point is really key for our alkalinity testing. Again, because we're making the assumption usually that we are looking for a concentration in terms of calcium carbonate. So that final ability to neutralize acid should happen around pH 4.5. So in summary for alkalinity testing, I wanted to just provide you all with this slide that demonstrates the full calculation sort of expanded so you can see all the steps. So we've talked about all the parts of this, so mainly this is just for your reference for future use. For this next example on alkalinity, I just want to go over what will happen if someone does want to report in a different unit. So we've sort of been hammering home that usually people want their alkalinity and water hardness reported as milligrams per liter of calcium carbonate. Well, this is an example of what can happen if someone wants their units reported in, say, milligrams per liter of bicarbonate, which can happen sometimes. So what you see on the screen are 2 different calculations, but they're using the same set of titration data. So if you look through, the mils of HCl are the same, the molarity of the HCl, and the amount of the sample is the same. What you'll see though is for reporting as bicarbonate, you don't have to worry about the diprotic base portion, and the molecular weight of calcium carbonate and bicarbonate is going to change. So you'll see that factor in there as well. Essentially, at the end, once you've calculated everything through, what you'll find is the same exact data, just depending on how you report it, can have, this is over a 20% difference in your final result, just based on what you're reporting it as. So again, usually everything is reported as milligrams per liter of calcium carbonate, but if someone expects, is reporting it as a different unit, you should expect to see some changes. Okay, so let's circle back to the question from the beginning of the presentation. Now that we've reviewed the testing methods, would you say that 100 milligrams per liter of calcium carbonate water hardness is equal or not equal to 100 milligrams per liter of calcium carbonate of alkalinity? The answer on that is it depends. So not really a straight answer on that one. But in the next slide, we're going to start to really dig in on a proficiency example and go over this a little bit more as to why it depends and what is the case that you can get these 2 values to essentially be equal. Okay, so this is going to be the final example of this presentation. And what we're going to do is review the water hardness and alkalinity of a mock proficiency sample. So essentially, if I wanted to test out our QC technicians, I could put together this proficiency sample and submit for them to test for water hardness and alkalinity. So in this example, our proficiency sample is going to be 5 grams of sodium bicarbonate, 12 grams of calcium carbonate, and 8 grams of magnesium carbonate, all dissolved in 1 liter of water. So if we go through and do our calculations, essentially what that's going to lead us towards, as you'll see on the right-hand side over there, is the sodium bicarbonate will give us about 1.3 grams of sodium. The calcium carbonate should give us about 4.8 grams of calcium, and the magnesium carbonate should give us 2.3 grams of magnesium. So if you run that through the calculations using that shorthand that we had talked about earlier, what you'll see is a final result of 21,514 milligrams per liter of calcium carbonate. Now, the interesting thing to sort of keep in mind is that sodium doesn't count because, again, water hardness does not include sodium. So that portion is going to be left out of the water hardness calculation. So you can see the green text there along the bottom of the slide. Again, that's getting multiplied by 0, whereas the calcium is getting multiplied by 2.5 and the magnesium is getting multiplied by 4.12. So in summary, water hardness in this, we should expect them to come up with a value close to 21,500 roughly micrograms per mil of calcium carbonate. Now let's take a look at the alkalinity calculation for what we would expect to find. So essentially for this, we're going to take the math from the last slide where we've converted everything over to figure out the amounts of sodium, calcium, and magnesium, and then take the remainder and use that to calculate what we expect to see in terms of grams of bicarbonate and carbonate. So essentially, if we do that calculation, we can figure out the number of moles of HCl we would need to react with that. And once we have the moles of HCl, we can calculate again what the moles of calcium carbonate would be to interact with the moles of HCl, and then convert that over to milligrams of calcium carbonate. And this example is easy because really all we need to calculate is the milligrams of calcium carbonate, because we again are dissolved up in 1 liter of water, so it can be milligrams per liter or micrograms per mil, again those equivalent units. So in this calculation, feel free, I didn't want to sort of make the slide real messy with a bunch of calculations. But the final alkalinity result in this one is going to be 24,477 milligrams per liter of calcium carbonate for our alkalinity result, our expected alkalinity result. And again, from the last slide, our expected water hardness result should be about 21,514 milligrams per liter of calcium carbonate. So you do see a little bit of a difference. So in this case, our answer of, would alkalinity and water hardness be the same? In this case, that is not the case. That would be not true for this mock proficiency sample. Now, where it can be true and where it's going to be a lot closer to truth is if the only thing in this mock proficiency sample would have been calcium carbonate. In that case, you can run through the calculations and you will get, pretty much the same number for alkalinity and water hardness. So just an interesting, sort of way the math works. So if your sample is mostly calcium carbonate, you can expect your alkalinity and water hardness to be very close to one another. If you've got other things in the sample besides calcium carbonate, you should expect to see differences in these two values. So to summarize everything that we've gone over so far, again, water hardness is really dependent on the concentration of calcium and magnesium. It won't matter what else is present in your sample. So if sodium is present, that will not matter. It really depends on calcium and magnesium. Whereas alkalinity is mainly dependent on like the amount of carbonate, bicarbonate, hydroxide. There can be other things in there as well that are not as common, but the ability to neutralize acid is the biggest point for alkalinity. So I hope this presentation has cleared up any questions you may have had on water hardness versus alkalinity. But if you do have any other questions, please feel free to submit them and we'll answer them at the roundtable at the end of today's presentations. Or you can visit inorganicventures.com where we have tons of technical support, or you can reach out to us directly. Thank you all for your time and your attention.